All right, so this is lab 4, and I need to start by talking to you guys about a little bit about what's sometimes called Taylor's theorem. All right, and so last lab we looked at the idea of a Taylor polynomial, right? And basically, a Taylor polynomial was the best polynomial approximation for a given function based at some point. And we figured out that the way to make the Taylor polynomial is to piece together, use the derivative of the function to calculate coefficients to this polynomial. And so we actually put together some of these things last class, right? Last lab, I should say. Let's see here. No, I don't want to open it there. I'm trying to open it in the... I think I just did it again. All right, well, here we go. Trying to open it with the Adobe. There we go. Come on. Give me fits. So we're using some of my notes here. And you notice this part of the notes is just appearing in lab, right? I don't actually intend to put this on your test. So this material is only covered in lab. It's not, part of the, wouldn't appear on the final or elsewhere. Let's see here. So this is the theorem that I want to talk to you guys about today for a couple minutes before we get into lab. Here it is. This is Taylor's theorem with Lagrange's form of the remainder. And what it says is that you can quantify so if we look at the function f of x on the interval from a to b, let's say, then we can write the function at b is equal to the Taylor polynomial at b plus this remainder term at b, where the remainder term is given by evaluation of the function, the k plus 1th derivative of the function times b minus a to the k plus 1 over k plus 1 factorial. Now, what this is essentially it's an analog to the mean value theorem. It says that the difference between the function and the k plus 1th, the k Taylor polynomial, it's related to the k plus 1th derivative. This is just like the mean value theorem says the difference between the function and, the difference between the function and its value at a constant is related, the constant would be the 0th order Taylor polynomial. So the mean value theorem says that the difference between the function and its 0th order Taylor polynomial is related to the 1st order derivative. So this is actually a generalization of the mean value theorem. And the proof that is given here, and I won't go through all the details, but essentially the proof is based on an argument very, very much like the mean value theorem. And so here it is. Come on. And so what is done is you define this number m according to this equation, like implicitly m is the number that solves this equation, where we have f of b and the function, its derivative, all the way out to k minus 1th derivative evaluated at a. And then I introduce a new function, g of t, which is equal to what this new function is basically is the Taylor polynomial evaluated, basically it's the Taylor polynomial minus f of b plus this number over here. And so you're able to show that this function g has g of b is 0, and also g of a is 0. So you have g of a is 0, you have g of b is 0. G is a continuous differentiable function. That means we can apply Rolle's theorem, all right? But the thing is, when you apply Rolle's theorem to this kind of sneaky function defined right here, it ends up giving you the result which I claimed, which is Taylor's theorem. So the derivative of g is kind of complicated because it's got a lot of terms. But after you sort through all those derivatives, you get this. And what did Rolle's theorem say? Rolle's theorem says if g of a is equal to 0 and g of b is equal to 0, then there's somewhere between a and b such that g prime of c is 0, right? But this function g, the derivative, works out to be this. And to say that this derivative is 0 somewhere is tantamount to saying that there exists a c such that the kth derivative evaluated at c minus m is equal to 0, which is precisely the result which is needed. And then getting to the point here. So anyway, just trying to give you a big picture that the way this is proved is essentially appeal to Rolle's theorem, just like mean value theorem was proved with Rolle's theorem. The argument really isn't too much different. It's just more complicated because it's for a kth order polynomial rather than just a 0th order one. But here's the thing we'll actually use, which is that this is a corollary to the Taylor's theorem I just mentioned. It says that if you have a function, and this is, so this right here is the Taylor polynomial of order k centered at a. So that plus this remainder term is equal to the function. And so the difference between the function and this Taylor polynomial, well, that's essentially the error in approximating the function with a Taylor polynomial. And so the error term is this remainder term, Ra, so k, sub k of x. And this corollary to the theorem says that if you can bound that error term by the constant m times L to the k plus 1 over k plus 1 factorial. Here, L is the length of the interval considered. And so what this means is we can bound the error in using Taylor polynomial using this corollary. So let me show you an example. So here's a function, all right? F of x is 6x to the 5th plus 15x to the 4th minus 10x cubed minus 30x squared plus 2, right? And so I can calculate the first derivative. We can see that actually 0, 2 is a critical point of f for what it's worth. You can calculate the second derivative. And when you plug in 0, you get minus 60, all right? And so this example here, so T2, right? T2 of x is f of 2 plus f prime of 2 times x plus 1/2 f prime prime of 2 times x squared. This is the Taylor polynomial for f of x centered at 0. And it ends up being 2 minus 30x squared, all right? Now, Lagrange's theorem, Lagrange's form of the remainder of Taylor's theorem, what I just showed you, is also known as Taylor's theorem with Lagrange's form of the remainder. It says that if you can bound the, hey, come on, my laser. Aw, man. If you can bound the next derivative up, which is the third derivative here, all right, if you can find a bound for that, then we can apply that remainder theorem estimate, the corollary to the theorem. So here, f prime prime is this. And so if I wanted to bound the third derivative of a function, why would I look at the fourth derivative? So here's something I haven't told you guys much about, but if we know that the function's increasing or if we know that the function's decreasing, think about that. That means that whatever the function if it's increasing, that means that the graph of the function kind of looks like this, right? Hey, come on. My laser's not working. The function kind of looks like this, right? So if the function is going like that, if it's increasing, then a lower bound is wherever the function starts and an upper bound is wherever it ends, right? So if you can show that the function you're trying to find a bound for, if you're trying to like pin the function between two values, if you can show that that function is either increasing or decreasing, you can use endpoints to find the biggest and the smallest the function can be on an interval. So in this problem, I want to figure out how to bound the third derivative. So I can, if I look at the fourth derivative, and if that's positive or if it's negative, then I can use the endpoints on the interval considered. So like I say, okay, I'm going to consider the interval minus 0.1 to 0.1. That's the interval I'm going to think about. And the question is, what's a bound for the third derivative if I'm on minus 0.1 to 0.1? Well, since the fourth derivative is positive for this one, right? If you look at that formula there, if you're between minus 0.1 and 0.1, that's like 360 plus or minus 72, which is clearly positive, right? So that means the third derivative is increasing over the interval minus 0.1 to 0.1. And so that tells me that I can put the third derivative evaluated at here and the third derivative evaluated at 0.1. Those are sort of bookends for the third derivative. Those are bounds for the third derivative. In particular, the third derivative is stuck between minus 92.4 and minus 20.4. So the m, if you will, the bound for the absolute value of the third derivative, we can choose to be 92.4, because that's the biggest magnitude the derivative can have on that interval. So it takes a little work. I mean, the point is, to use this corollary, we need to find a bound on the derivative of the next term we're not using. Like if we're looking at the kth order Taylor polynomial, we have to look at the k plus 1th derivative, find a bound on that. That then, through this corollary, tells us how to bound the error. So it's a little bit complicated, but it's something we can do with the technology that we have. So here's a picture of what I just said. So what you're looking at here is the bound. If you plug in the bound I found into the corollary, we end up with an error of 0.123. That's like a upper bound on the error. So this graph right here is plus or minus 0.123. And so the red is the function, I believe. The green is the second order Taylor polynomial, right? And as you can see, not only was Lagrange's theorem correct, like certainly the function is within the error, the tolerance that the theorem prescribes. In fact, that error is very, very generous, right? It's actually much closer than that, we can see graphically. So part of your lab is to create a picture similar to this for a function in the lab. All right? I'll show you another example. Sine of x. Actually, I think in your lab, I have asked you to do something with sine x, actually. This is very relevant. So sine of x, if you think about derivatives of sine of x, what do you got? You got like either cosine, minus cosine, or minus sine, right? So what is a bound on the derivative of, or what is a bound on the derivative of any derivative of the sine function? Well, it's either plus or minus sine or cosine, right? So what is a bound on sine or cosine? Like what's the magnitude, the farthest the graph of sine or cosine can get from the x-axis is what? Yeah, 1 and negative 1, right? So the m in the corollary, we can just take to be the number 1 for these. So finding the bound is much easier for sine or cosine. And so I put in the 1, and I chose to look at minus 1 to 1 from my interval. And so a bound for the error in the kth order Taylor polynomial would be 2 to the power k plus 1 over k plus 1 factorial. And I again illustrate. So like here actually is a, come on. The third order Taylor polynomial centered at 0 is this, x minus 1 6x cubed. And what I have graphed here, though, in particular is, I can't read. I think that's T3. So I think this is actually essentially the answer to one of the parts in the lab, but I want you to try to work back through that for yourself. Here's another one. This is a graph of the 9th order Taylor polynomial for sine, along with the error bar that Lagrange's form of the remainder appears. As you can see, it does fit within the error bar. Now, I'm not actually sure what's the best way to graph those error bars. We're going to have to discover that for ourselves today. I used a program called Graph to create these pictures, so I know there, but Graph is like freeware. If you had a personal computer, you could put Graph on it. It's like 5 megabytes. But these computers, I don't think we have administrative privileges, so I don't think we can put Graph on them. Let's see here. And then I also have in the notes here a note on like why the formula F equals mg. You know, in physics, we use this approximation F equals mg for the force of gravity near the surface of the Earth. But that's actually an approximation for gmm over r squared, right? And in fact, whenever we use F equals mg, we're using the 0th order Taylor approximation for the for this function. I'll put it up here. So like Taylor polynomials are used throughout science to replace complicated formulas with easier formulas. Like this is pretty complicated, right? GMM over r squared, come on. I think I've gotten chalk inside. I've been carrying these lasers in my chalk bag, in my bag with the chalk, and I think the chalk has gotten in there. So this is Newton's universal law of gravitation. As you can see, it depends on the inverse radius squared, right? But when you do physics, you just oftentimes, for problems near the surface of the Earth, we use F equals mg, right? That's actually an example of using a Taylor polynomial. Mg is the 0th order Taylor polynomial for this thing. So like this is the real formula. F as a function of altitude would be gm. This is the mass of you or me, whatever that we're talking about. This is the mass of the Earth. That's Newton's gravitational constant. This is the radius of the Earth, and that h is the altitude. So this is the nonlinear function of gravity. But we approximate that by just basically f of r. Or, well, f of 0, because I'm using h for altitude. So f of h is basically f of 0 plus an error term. So f of 0 is minus gmm over r squared. And that actually, this gm over r squared is about 9.8. That's that little g we talk about in physics, minus 9.8 meters per second squared. This other term over here captures the error in using F equals mg. And if you work that out, it shows that the error is something like linear with altitude. And you know, if you crunch some numbers here, you'll be able to see how wrong using F equals mg is. I worked the numbers out here. Basically, the error, it scales like your mass times altitude times this constant, 3.1 times 10 to the minus 6th, right? So what that means is if you're like, you know, if your mass is like 100 kilograms and your, you know, altitude is less than, you know, say a kilometer or even 10 kilometers, this is pretty small. But if you get up to like 100,000 kilometers, like if your altitude gets up to like where our like really, you know, high-flying jets get to, you actually start to get a, you know, maybe like 0.1 meters per second squared or something like that off. So the approximation F equals mg, that's only for the surface of the Earth, and the further you go out, the bigger the error gets. This theorem I'm telling you about today, about Taylor's, you know, Taylor's theorem, what our lab is about, actually is the mathematics which allows us to quantify I think it's that time of the morning. It should be time for my extended warranty. Oh, nope, nothing, just nothing. Fun. So let me get the lab out here. So our lab has basically 3 parts. The one is to understand theoretically how Taylor's theorem allows us to bound the error generated by exchanging a function for its Taylor polynomial on a closed interval. I've tried to explain that to you now. Then we're going to illustrate Taylor's theorem visually by graphing both the approximating polynomial and the potential error band for a given function and interval. I showed you some examples of that in the notes just a second ago. And then we're actually going to find the interval for which a given Taylor polynomial approximates the function within a particular tolerance. What we need to do these things are both Wolfram alpha to take derivatives and Desmos to actually look at some graphs and to find some bounds. So part number 1. So the error, basically the way this works is we have to find this constant m, all right? Oops. I wish this wouldn't, I hate the way it, I want to look at it, there we go. So this right here is the difference between the function and the Kth-Taylor polynomial. The theorem that we're working with says that that error is bounded by this number m times 1 over k factorial times b minus a to the k plus 1. Here, a to b is the interval on which we're trying to approximate the function. And the theorem simply says that if you can find a bound on the k plus 1th derivative of m, then that serves to bound this error according to this rule right here. So number 1, I want you guys to figure out what is the third order Taylor polynomial for inverse tangent, all right? So part A, you need to find T3. Then I want you to find the 4th derivative, right? Then I'm going to want you to find a bound for the 4th derivative, all right? And then we're going to try to recreate that kind of picture that we did, that we looked at in the notes a second ago. And so that's part 1. Part 2 is you're going to be trying to figure out what interval minus c to c is this approximation correct to within an absolute error of 0.01. And then same answer, same thing for here, but the function's 1 over x for equal to 1 minus x. So here's the difference. Number 1, I'm giving you a function, and I'm assigning you an interval minus 1 to 1, and then we're trying to quantify basically how much the error is in using the third order Taylor polynomial on that interval. In contrast, number 2 and number 3, I gave you the Taylor polynomial centered at 0 for both of these, and I'm asking you how far can we use this if we want to have an error of no bigger than 0.01. So like the structure conceptually of 1 versus 2 and 3 is a little bit different, but that's the whole lab. So I'll let you guys work. And I will come around and help you if you want help.